As already said, my name is Michał Łoś. Today I would like to talk with you about my adventure with some kind of a framework, about which we'll talk. The link to the repository where the code will be, but it's still not yet, will be at the end. What I would like to talk about today is something. Basically, I had quite a lot of fun doing it, designing it, implementing it, and writing some features. And I would like to share today that experience to entertain you and also maybe inspire. We're going to get some dive into the design process, the architecture, because as Kenneth Henley said, architecture is set of small decisions. And those small decisions have sometimes very big impact on what you got in the end. I was surprised with what I've got, so this is the result. I'm going to show you also quite a few tricks, and I hope you will enjoy that. Okay, so let's start with agenda. I hate agendas, so I will make it functional. Functional because are there any people here who think that this presentation will be about Java in some greater amount, in a little bit? Hands up, please. Okay, not many, I see. So if you think that this will be about Java, I need to scare you off. So let's declare the agenda as a meta list of certain elements. The motivation, the initial design decisions, where we'll say a few words about our goals and what we want to reach, what I wanted to reach when I started to design this framework. After that, we'll talk about how does thing works internally, and this is a bag of different stuff. I didn't want to split it too much. We'll talk about caching things at runtime, and we'll talk about compilation optimization. There will be Q&A, if I will manage to finish this in time. Okay, guys, so to scare off all the Java guys even further, let's start with motivation, which is actually an eager head of the meta list agenda. This means that basically this is just motivation, the first element from that list. Some 15 years ago, I wasn't there at that time. Some guys decided to, in a project in which I started to work much later, had a design of a receiver service to which some client libraries sent notifications. Basically, very simple. There was a server and some clients that were sending messages to it. There were two scans of that library, one in Java, one in C++. 15 years ago, they probably were too scared off to do it in a different way, so they decided that they would just repeat the implementation in two places. Yeah, they added some very bad transport layer, which at the time maybe was reasonable, but I doubt it. So the question is, what could go wrong during that time? Well, pretty recently, when we started to work on that project, it became obvious that one library is a terrible mess, second library is a terrible mess, but a little bit different one. Because, yeah, when you fix things, then, yeah, it can slip away some changes. So this one works slightly a little bit different than the other, right? So we wanted to clean this up, obviously, to basically, first of all, to get rid of that terrible transport layer. That was our main goal. It produced a lot of problems. It's too embarrassing to say how it works until you ask me directly, but so I won't tell you. So the process of cleaning this up was to first move all the calls from C++, because C++ was used here just as an addition. Most of the code was written in Java, so it is reasonable to rip off everything from C++ and redirect it to the Java library, and use internally. Then, because C++ part would be cleaned up, absolutely cleaned up, clean up the mess in the Java library, after which you could basically get rid of that awful transport layer, right? Yeah, so we decided to write it down. And when we started, then you have to face something called JNI, which is Java native interface. It's an interface for a C language to cooperate with Java Virtual Machine, which is also implemented in C, I think. Sorry, it depends on the implementation, but so given such code. So you have a my class, some method that takes string as a parameter and doesn't return nothing, called my method. In order to do the call in the JNI version, you would have to first, given some obvious environment stuff that you get from a different way, that doesn't matter, you have to first create a new string. UTF. Java uses a very specific version of UTF-8, and it actually requires some parsing, but this is the simple version. After that, you have to obtain the class pointer identifier, actually, because it's a runtime entity. Java needs to know this as an object. So this is literally the Java lang class object. Then you have to obtain the method ID for that class. Method ID requires class, name of that method as a string, and this weird piece of letters that basically is a function signature written in Java. As you probably see, this means that here are the arguments in the brackets, and the last letter is V for void. I think the byte is a Z letter, capital Z. So yeah, that looks nice. And we still even didn't call anything. So we're calling something using all those arguments and using the appropriate method from JNI. You see that there's a call void method because the return type is not involved in method overloading, so it has to be a separate method for all the basic types, which is cumbersome, basically, to selecting it. And don't forget to release that string that we already allocated after call, right? Yeah, so it's ugly. It's ugly, and it's definitely not something that you would like to write when you have some kind of a framework that you want to upkeep and maintain for some time. So we decided that we need to wrap it in something smarter. So let's start with initial design decisions, which are declared as a eager apply of some meta function called pipeline, which is basically basically we on the vector agenda we call first we call drop 1, and for the result we apply first off. So we're dropping first element and take head of what it left, which returns the initial design decision, of course. So there was, I already knew a better way to use and work with JNI, which was Qt for Android. And in this framework, this particular framework, it does things much nicer. First of all, this is basically the object construction. You use the type Q Android JNI object, and using constructor to which we have to still pass a string saying where is the class in a class loader. But this is also a call to a parameterless constructor, which is nice. Our string is also wrapped in RAII thing. But by the way, why some shortcuts in C++ are called like sphin are written as a word, and RAII is not. It's like, I don't know, it's reminded me the sound of a seal. I something. I don't know. Well, okay, RAII wrapper for a string. And the construction here is very simple. This is nice, actually. We don't have to remember anything about allocation, and it's exception safety, of course. In order to call something, we have to call the method on an object, so we don't have to pass it specifically, but still we have to use the method name as a string as well as its signature. And here is our parameter as a QAndroid object, not some JNI internal. So Q for Android achieves one point, that it hides the complexity of JNI calls with some nice wrappers. So we can do a different call to a different method, which signature begins to grow and grow. This is the method that takes Java long string, and don't forget this is an I for integer, and returns another string. So you can imagine that if the method needs some longer class name and some more parameters, this becomes very tedious to upkeep, and it's very easy to make a mistake because you have no support from the framework to do something wrong. You'll be hit at runtime when you do something bad. So again, first of all, we would like to get rid of these in some way. Second thing is we would like to get rid of these, because this is also a string. Moreover, we would like to merge those two into one entity. You can save them in some kind of a string constant or something like that, but you still have to pair them manually, right? So it's not a method here. And last but not least, we still have to remember about our class path. Everything we write here is put into QAndroid JNI object, which is very general object, which doesn't know what method it has, even though we could place there some information about what kind of Java type would be there. So it begs for some abstraction that will help us to manage this thing. So we have basically two sets of goals. First one is that given those three informations from user, that is Java class, Java method name, and JNI method signature, given those three informations, we would like to, and given some C++ parameters, we'd like to do some conversions of those parameters into JNI types, then call some appropriate method and passing there all the information that we need, we've prepared previously, get the result, and turn that result into C++ type, and basically do all this highlighted thing automatically. Do this for user. Let him just pass us these three informations and this information in some nice form, and we will do something for him. Second goal is a compile time goal. We'd like to add some logic there. So we'd like to do a binding of Java class and its methods in a way that you won't be able during compile time to run those methods in the wrong way. The same thing applies to the method name and its signature, and basically generate those awful signatures. Why we have to write them down by ourselves? This is something that is ugly. So one last thing that I should mention here is to not require external code generator. Why is that? There are two reasons. First is that code generators, just mess with your build system. Usually, code needs to be generated at some point. It usually makes the compilation longer. Generators tends to have bugs or things like that, and sometimes you just want to do something quickly. So it would be good to be able to easily write the write our description of all those things above manually. And if we do this approach, this will actually, it still doesn't mean that we can't use any code generator. We can then write something else, but only if you wish. It makes this optional. So here's our holy grail. We want to be able in C++ to create an object in a way that doesn't differ from any Java object, which doesn't differ from any object in C++, to be able to call any method of that object and be sure that we are calling them with appropriate types. And lastly, get some results from other calls, maybe. And making these results here should be a string, right? Yes, my different method returned it a string. So, yeah, this is the goal, right? Well, not that fast. The construction is a bit problematic because if we allow user to create object at any point in time, then it means that it can call any methods before even Java Virtual Machine starts, right? So this means that yeah, he will hit a runtime error. We wouldn't like him to do some runtime errors. So I will address that further. So let's get to another section, how things works in CPP JNI. And another beautiful algorithm here. This is actually, I'm cheating here a little bit because I'm applying still to our agenda this algorithm, which is a filter which searches for exactly known class. And in fact, it returns a list with one element rather than just single element. But it's actually true because this is a bag of different stuff anyway. So, okay, let's put ourselves in the pants of a guy who would like to write something that we want to create some code that will run internally some JNI code, in fact. And we'll think about later how to make our user use less code, in fact. So we'll wrap some things in macros. But right now we will focus on how this code should look like in the end. So what we need, definitely, in order to call my class as a C++ entity, we definitely need something that has some struct, some class that has a name, my class. Why is that? Because in C++ there's no reflection, and we cannot eject any name during compilation time. Those names have to be already there, which means that we need a name for our class, and this has to be a class. There's no option here, unless we use some macro magic, which I hate, and I'm trying to use this as less as possible. What's more, we need also to put here a name of our method. Doesn't matter what those quotation marks are, because simply for very same reason. If you want to call a method on an object, you need to put that name, whether this is a function object or a real method. You have to put a name here. So this is the starting point, right? So maybe we should allow something like that. So in order to declare our method in C++ that maps to the method in the Java class, maybe we should just simply allow here C++ types and then map them one-to-one into Java types and be happy. I think this has some problem, because if you take a look at this level, we'll focus right now on these parts, basically. There's a certain mapping of types that we are doing. The simple version is that we just simply map this type into this type. So when user uses int32, then it will map into Java int, right? This very similar thing happened, for example, for a string. If we have those types, we can map them into std string. But the problem is that when we want to, when we will have a type in Java that is car array, actually it should be something like that. Maybe a vector of car. Don't do that at home. The string is better for that. But maybe vector of car is actually better than this, which means that we just broken our mapping. There's no one-to-one mapping between C++ types to Java types. So the better approach is to do it absolutely differently. So is to focus on those Java types and map them, allow them to be converted from some set of C++ types. So we need to add an abstraction. We're adding abstraction here by let's add abstraction by just putting. Oh, we also need to we need to allow our user to be flexible. So he could also add his own mappings for his own types in any way that he wants. And if we fix some types in C++ into Java types, then we will have a problem. Our user will have a problem extending this. So maybe instead of that, we could put some special types, like here, void, like this string, right? Think about those things above as macro parameters that we'll pass there. We want to limit them because user will have to write them down all along, but these will be definitely used. So, so when we wrap this method in a macro, it will take these things above, and there's a problem with that, of course, because we had a function that returned void, which is nothing, but right now it returns something, and our user can think that, oh, so this is a void object. Maybe I should take it as a value and check it somehow. This is stupid, but yeah, you could do that probably. So yeah, maybe we should do it differently. Maybe we should change it into auto and do some magic here in order to return some C++ type instead of special mapper type, which will probably, like the string, have conversion operators or constructors that will do the thing. This will, of course, this way, we will mess with our macro because we have to somehow generate those parameters names in a macro. And believe me, you don't want to do that in a macro. Macros are dumb, really. So the only option that we've left, if we are so constrained, is to actually abstract out even the arguments. There's one other thing. Our string here would have to have a state, so it would have to be an object which will be converted from some set of C++ types, and then it will have to keep this Java string internally, which is not good. This is not nice. Someone can take this type and, for example, try to use it as a normal variable. We wouldn't like that. We wouldn't like our user to do that by mistake. So there's only one option. We have to make this a template. Basically, this is like saying for C++, yeah, this method can take everything, can return anything. We'll deal that internally inside. So this means basically that we need to do some meta machinery internally in order to, given those things that will be passed to our macro probably, that will do all the conversion for ourselves, right? Okay, this sounds like a challenge, but it's doable, definitely. So let's take a look at our string structure. So what it needs to have in order to be some sort of a set of information in order to do the proper conversion and conversion from and back Java. It first needs a signature. Let's say that right now, just for the sake of simplicity, this would be a carstar const expr static, which is actually natural to put something like this here. It will be used then to generate the function signature for JNI. Another thing that we need is we need to check it at compile time, whether our argument is actually convertible. Remember that we are allowing our user to drop any types to the function, and we need to check at compile time, is this argument that he passed to us is actually convertible to the type that was placed there. So we are, this way we are adding a constraint that user, when he provided some signature for our function, wouldn't pass some things that can't be passed to the JNI. So we're adding some compile time checks for the signature. Another thing that is necessary is some convert to JNI function and convert from JNI function. These both are static, and we reached our goal. This class doesn't have any state, doesn't have any weird constructor, so these methods would be used internally to do the conversion, appropriate conversion. Very similarly, our void type have some signature letter. This is that V, and because void is very special, it needs to be treated in a special way. We want to constrain our user from putting voids into the function argument. So we're doing something like that. Who knows why the size of t is placed here? Why this strange thing here is placed? Who knows? Hands up, please. Okay, not many of you. Good. As you see, this is a template. So compiler compiles it twice. First time when he sees it, in order to provide, doing the first pass, he wants to know what he can, he wants to calculate whatever he can. In order to do, when you have a final instantiation of that template, he would have to compile less. Moreover, he can check the code here. The only compiler that's up to very recent version of Visual Studio didn't do that in the 2 steps. It does it in the 1 step, but Visual Studio is weird, so doesn't matter. But normal compilers always did that in the 2 steps. And in order for it to not static assert whenever he sees that template, is to bind the static assert value to make it undeduced context. Make it by making this static assert valid only when we will pass a proper type here. So basically every time this type is instantiated rather than declared, this static assert will run and will fail the compilation, which is actually fine because this means that someone is trying to return to pass the void to an argument, right? Simple trick. So let's so we can wrap this everything we set up to this point. We can wrap into macro, which looks simple. First parameter is a name. Then there's a return type, and then some bunch of parameters that will be passed. Okay, so far so good. We can work at that. We can do something. It doesn't matter what will be inside of the this macro right now. But let's add something to the equation because the complications is something that that is normal. Let's say that given our class, we're going to add a different my method, which has the same name, but a different signature. Right now it takes an integer. What does it mean? It means that if we will declare it this way, and remember that beneath there's a template that takes the random arguments, you'll basically get a compile time error. It depends. I think it depends on, no, it doesn't depend on compiler, but it's ugly and I'm not going to show you. Basically, you have 2 functions with the same name and possibly all of them can take the same arguments from the compiler point of view. So he will probably get the first one, and in the 50% chance he will fail. By never getting to the another, or maybe he will say that there is some ambiguity in definitions. One of those 2, I'm not sure right now, to be honest. So no, we need to do something better. We need to do it differently, and basically this is the solution. You can use function signature types as one entity, which very nicely fits into our macro, and pass it to the macro. So macro is a series right now of function types, which is nice. This even look good. Sorry, this even looks good, right? You probably see something like that. Okay, so let's go further. Let's go further. Let's go inside this macro. What kind of code this macro should produce? So there will be definitely some template method. It's const by design, and returns some auto, takes some error value parameters. And inside, it will still need to use its name. That's why basically this is why we need macro here, because this method name is used here twice, and there is no escape from either using it twice or using the function standard macro, which returns the function name. It's the standard function macro, dash function dash is standardized, but its implementation defined how this will be created. But I've checked, every compiler uses the same thing, but it still would be too much for a user to ask user to write every such function this way, because yeah. So it's better. It minimizes the amount of information that we require from our user. So we used macro. But what's the next step of our function? This macro basically internally right now, this macro is a bit more complicated, but there are some details that we just make us distracted. So basically, I've created something something called method caller that takes a bunch of meta information about our class, method, etc., and which have a method call that takes this object, its name, and passes there all the arguments. Something like that. Well, the problem is that what's happening actually inside the call method. In call method, we need to do some overload resolution. So this means that we need to take all the function signatures and select the one that is right, correct? So we have some overload resolution algorithm there, which is a meta algorithm, and basically I'm going just to do it very quickly. This is an algorithm written in the same manner as my slides, where there was some operation on agenda, and it contains a pipeline which is basically a set of algorithms executed one by one. So it's first filtering all the past arguments by arguments count. It counts just the number of past arguments passed to the function and checks which of the signatures actually have the same amount. It's a very simplified version, by the way. And in the second step, it tries to find the first one that will be able to convert all the past parameters to appropriate JNI types. Simple, right? By the way, this template thing is, I heard that those templates are called, when some speaker doesn't want to get into details of how those templates work, he calls them ponies. So I don't think these are ponies, because if you take a look here, this is something like a mouth, and it has 4 eyes. So it's definitely some kind of a dragon, I would say. So these are the dragons, right? I'm showing you right now the dragons, so don't be scared. They're scary just by design. Once we have our algorithm, we should apply this algorithm to list of our all overlords. Sorry. So this algorithm is applied to this list, and result of this algorithm is passed to the MPL optional, to basically some meta optional, which we then can check in a static assert to inform user that he passed some wrong parameters that we are not able to recognize in the list of function signatures. So So this is the thing. And how does the calling the actual function looks like? Basically, we have to prepare our arguments, do the conversion. Once we have converted arguments, basically it's easy. It's just a selection of the appropriate environment method. So here's how it's done. So we first select the declaration of function that we prepared in the previous step. We create converters. I did a little bit of simplification. It's not just a simple function type. It's something that wraps around it and extracts some information from it. So it has something called arguments t, which is a HANA tuple. It's just a tuple of argument converters. It's a compile time entity. So we can write const expr here. And the same thing we do with passed args, arguments passed to the function. We make a tuple out of them. HANA is actually right now, from my knowledge, is the best thing to do the heterogeneous programming. So I really recommend using HANA for that. And when we have those two vectors, converters and appropriate arguments, we just need to do the conversion using HANA zipwith, which means that we take pairs of passed args and converters elements and apply them a function, this lambda function, which simply runs convert to JNI on every argument using the appropriate converter. Yes, this is the part of the actual code and looks simple, right? Yeah. I like scaring off people with things like that. So basically, we're almost there. But let me add one more thing. So we have that overloading mechanism, simple overloading mechanism. But there's one more thing that could be here that you should probably think of. So this is a static word, right? Static method. Well, actually, at first I thought, yeah, whatever. It's just the same function, almost. There's a need to put that information somewhere, but we can make this our function in our interface static, right? Well, not really. Actually, this is fine because in Java, this is how you call the static method, and this is a normal way to do that. But also, you can create an object and call the same static method using object instance. This is a warning, the compiler warning, but this is fine. I have no idea why they made this idea, but I don't like it. But this is how it works. In fact, this object here doesn't matter at all. It just provides the type information about which type is the static method comes from. And to my surprise, exactly the same thing. Actually, I was more surprised by Java than by C++. In C++, doing ugly things is normal. You also get some warning that you're doing something not really nice, but it's okay. It works. It works as expected. There's no one dead and everything's fine. But with my framework, this was a problem, because if you have a program runtime, during the program lifetime, this is that arrow, nice arrow here with T. The JVM, Java Virtual Machine, will be executed at some part of time. So, but if we allow these methods to be static, this means that basically there will be a runtime error if user executes this method somewhere before the JVM starts, which is not nice. We'd like to prevent that. And in my opinion, actually, I will just show you, we can prevent that by design, which is good. How to do that? Let's make a class an actual object created by Java Virtual Machine instance. This means that when you create the Java Virtual Machine instance, this is the only point from which you can create the actual class. There's no way that the user will use the class before it's obtained from the JVM. At least without any, you can do everything in C++. You can break any rules. So there's definitely some way. But if you're not ugly, and if you play by the rules, then this way you will never call the static method. There's one thing that so what we need to change in our current state of the framework. We need to pass this information into my class, make Java methods macro, by decorating our signatures with something like that. Well, it's not maybe not the prettiest way, to be honest, but it serves its purpose, and it's not even too much text. I could choose a different name, but I didn't want to because they're already in some namespace. This is not a macro. This is just a type that it's wrapping our signature. So, moreover, I said that we need to create at first we need to create a class object in order to do something, to call some static methods. So there's a different context in which this whole struct is executed. So there are two contexts: the object context, scope, and the class scope. So in order to provide that, the idea is to add abstraction. Make that struct, turn that struct into a template that derives from something that will pass it. This way, we can inject a scope to our class. So how does it look like? It means that our user declares some my class as a template, and our framework is doing something like that. It, depending on in which context it was called, it provides this template some base class, some object scope, and class scope. Class scope contains JNI reference, object scope contains JNI class plus object reference. And at the bottom of it, we are providing some wrappers around our class. So the purpose of that is to do some cleanup, provide some end constructors, or delete some of them, basically, and provide some nice syntax so that the user will know whether something is an object, something is a class, and won't be confused. Both of these are non-copyable on purpose, because we are not going to allow to do some. There are no copy constructors in Java. There's something that looks like, but there are only references, and we would not like to our users think that copying C++ object works as in C++ when it doesn't. So user have to deal with it by himself, basically. So when you getting back to our code, this is basically what here we have auto. My class is of type auto, but what kind of class this will be returned by the framework? It will be CPP-JNI class of my class. It's maybe a little bit more letters here, but in fact, you mostly use probably an auto. But if you wish, this is how it's done, and it's not very painful. When you need to construct an object, you're using my class and call it construct method. I know calling methods with the capital letter is maybe Microsoft likes it. I hate it, but this method has to be special because this is basically for the same reason. I didn't want to allow user to simply call the static methods. For the same reason, I didn't want it to use constructors. So I didn't want to also overload the new operator, for example. New operator could be used at any point in time. So this is so there was a need for some method, and the construct is the best name I could think of. So yeah, sorry. So this, of course, will be changed into a CPP-JNI object of my class. Okay, so let's talk about things that happen in the runtime a little bit more. Actually, yes, the caching is basically eager apply of some algorithm on the agenda, and we are dropping first three elements from agenda, and from what's left, we're taking the first element. Simple. So caching. The first question is what we need to cache here, because Java machine is a virtual entity. A runtime entity. Java virtual machine is executed at some point, and we need to obtain some data from it and store them somewhere. in order to not call every time the find class, the find method ID. So these are the things that we need to cache. First of all, are Java classes. Second are the Java method IDs. And maybe we should also cache the method signatures. This might be, the question mark here is on purpose. You will see later. So the first basic idea, I think most of you will agree that when you think about caching something that is a Java class, internal Java JNI object, is probably some unordered map that will take string as a key, and this is my my wrapper around JObject reference. So we can just put here a string which will contain just a class path, full class path, and get that reference. The very similar thing can be done for method ID, which is basically a int, and yeah, only here this string would be a little bit longer. The problem I have with that was, hey, I have so many informations already. I have information about the class names at compile time and about mapping between those all those things. Maybe I could do something more compile time. So what information exactly we have? We have first strings that name our classes at compile time. We have their method names also as strings at compile time. We know them that they're static const for const cars right now, right? And we have their signatures, which either can generate a method for creating them, or we can make them already prepared in some way. So what we need right now, I used the const expr car star for all the names on purpose, because this is not what I use. This is what you actually need in order to make it full compile time entity. You need a compile time strings. How do they look like? Yeah. What if we could use all those things? Well, these strings looks like this way. They are basically structs that take a bunch of characters as a template parameters, and somewhere internally have the const expr car data array in them. So this looks a little bit weird, but this is right now. This is a bigger discussion why this way and not the other, because you cannot put a string literal as a template parameter. This won't work for various reasons. Unfortunately, yeah. I hope so. I really hope so.
I am telling you this as a sure thing.
Okay, we've got someone from committee here. So, so in 2000, in C++20, this will be possible in a much nicer way, I guess. But I think it's something fresh, very fresh information. Okay, okay. Thanks, Michał. Right now we have to deal it this way. So, because if you don't want to wait to 2020, you have to do it a bit differently. What we want to achieve is to have some string type, declare it in this tedious way. I know, which we will make an ls for that, and declare the second time the same type, and have this invariant viable, which will not fail us in compile time. Basically, this means that we want to have we want to declare a type which is depending on the parameters always the same, regardless of which compilation unit sees it, etc., etc. Fortunately, this awful way of writing it can be changed into some sort of macro. This macro is one of the ugliest things I've seen in C++, because it's error-prone, it's ugly, and requires additional meta-programming mechanism in order to clean up the string that is resulted by that. But let's right now assume that it produces exactly the same thing as this one, okay? So if we have such string, what could we do? We can first change our const x car signature, which is just an address in memory, basically, into something like that, which is compile time information, which is not necessary unless we use it. We can, this is something I haven't told you, but we also need the class path information inside our structure, which is also reasonable, basically. And this also could be done and used in compile time. And finally, we could use the same, the method name that we used previously as a, not as a const char star, but as something that is compile time, which means that we basically can put it into meta information rather than, as it was previously here, runtime information, which also enforces some runtime checks, compile time checks, etc., etc. So yeah, okay, let's use it, right? So we can write, so for example, to obtain or cache our Java method ID, we could use something like that. This is some kind of, let's say, global method right now, which is a template, which takes a class path, method name, and method signature types as a string types, and have a static variable here, which is a Java method ID. This is basically a lambda that will be executed only once, which contains the procedure to produce this method ID, basically. And great, yeah, this will be created once the user will need it. Internally, of course, by the framework, but it's a very valid cache. I've checked that those method IDs are very predictable and are not some kind of pointer, they're just indexes of a certain method inside of a Java class, at least by Oracle JVM and the Open JVM implementations. So they're very similar in this place. So it's fine. And the same thing we can do with the class, right? With the class reference. We also can just make a method that is specialized by the class path and returns some global reference to this class and have some procedure here that will be executed only the first time we need it. Brilliant, right? Neat. Well, not really. There's a problem, which is not visible at first. Because if you have your main started, you know that things happen before main, some things happened before main, and some things happen after. So if you declare your JVM as a global object and try to obtain a class using that JVM somewhere, let's say, inside of the main, so in this place, it will be destructed shortly before the JVM, which is fine, and everything will work. That's nice. But we don't want our user to, we don't want to force our user to create it only as a global variable. JVM shouldn't be a global variable. Normal, good programmer puts the JVM into the main, where he can, for example, use the runtime parameter passed to the executable in order to execute it. So he probably will do something like that. But this doesn't change that my class reference, JNI class reference, will live much longer because it's created as a static variable. Why is this happening? Basically because this, of course, end of its life will try to call the JVM, and this will end up with an error. It's not a total issue, but I was really angry that it doesn't work this way that nicely, because it adds some additional checks for our Java class. So we need to check if JVM exists in the places which you shouldn't actually care of. So what to do? Well, let's start. Let's have a short lesson about how the memory is organized in a C++ program. You probably know that there's some code assembly placed in the memory which you shouldn't touch, and you don't. This is not your thing. There's a stack. Every C++ programmer knows that there's a stack, as well as heap, and basically we normally use only these two. What you may be missing, maybe not, but I still will tell you. There's some additional initialize data segment, which comes from C and basically used for everything that is, for example, the const strings are put in this separate segment of memory. And something that we're most interested in, initialize data segment called BSS segment. This segment of memory is used to keep all the global variables that needs to be initialized before main, and some local static variables, which also will be initialized, which can be actually initialized at any time. What's more than that, it basically works similarly or identically to the stack, which means that once something is initialized, it needs to, it will be deinitialized last in the last place, but using the separate stack after main during the std exit to be specific. So what does it mean? This means that we have two stacks. That's why we have the problem from the previous slide, right? And but we could use this BSS segment for our purpose, especially that it's basically link time calculated. So the compiler, linker actually, can calculate its size beforehand. It's a pessimistic size, but still valid. And how does it look like? Well, when you create something in main, it's a global variable. Then, when we create, for example, a local static variable, it's created during this. It's put on the stack on top of it. Oh, sorry. And some static local variable which can be declared at any point in time is also placed above them. And then they're removed from the BSS in exactly the opposite order that they were put. Simple. So how can we use that? What we would like to achieve is to be able to gather all the static globals, local statics or static, any statics basically, at this point in time. And for example, in the case of global class references, remove them, release them, and clean this up. So they will just be a bunch of information that are empty and can be removed by after the process ends. So how to do that? I think I have a nice idea how to create this thing. I call this a static map. What's a static map? It's a monostate that's created from that basically looks like a, you probably on your studies, I don't know, in high school you probably write singly linked list in C-ish singly linked list. So basically, static map from this perspective is identical. It has some static head. It's static because everything will keep in static data, so it must be. But this node will point to the first element of our list. And what is a node? Node is basically contains two elements. Of course, our element that we want to keep in this list, kept by reference, not by accident, and some pointer to the next element, and specific constructor. This constructor actually injects itself to the head of our list. So every time a node is created, it injects itself, it pushes itself in front of the head. Head starts to point to it, and its next pointer is assigned to the previous head value, right? Simple, very simple, trivial list. So this way, we can write, having this, we can write a getter function. How will it look like? First of all, it will get some key. This key is not a runtime time information; it's a compile time information. It contains two very important things. Which first one is value type field. It says what kind of type is actually stored by this list element. So what we do is, we're using some alias for it. Then we take we use the key type for a second purpose. This purpose is to use it as a constructor of our element, actually. So we can in fact create something a little bit different or use some procedure to produce our element other than its own constructor. So then we create a node. The node that takes also, of course, this one is static. So it's a static local variable inside of a function, Scott-Meyer's singleton. The same thing we do with node, but to node we pass the previously created element and, of course, a list head in order to inject our new node element into the list. And we, of course, return the element as a reference. Note that these two things will be executed only once during the first call to the get method. And then afterwards, every call will just skip to the return and return a strong reference to it. So let me show you how it looks like during runtime. So first of all, we'll have our head created somewhere on a stack, and now someone calls to get using some key type of x. So this means that we'll create our element type at this point at first. This is of course size of a BSS segment, and then we'll create a node. And now we need to put our head to point to our new node. Then someone else could call our getter to using y key, which creates another element type. Which creates another node, which will first point to the current head, and then we'll move our head to the new element. This way we create a linked list of all the elements that are on our static list, right? So this ends up with code that looks like that. I said this is a monostate. Monostate is a type of singleton that doesn't look like singleton, but it is. So our map, static map, in fact, we'll use the global reference to J class. And in order to obtain a new element, we need to call the getter to the class, something I call class loader, which simply loads class from J and I. This class loader then will initiate, when first time called, will initiate our class, and afterwards we just obtain already created reference. And somewhere in virtual machine destructor, we have something like this. This is basically copy paste from my code. So all we need to do is to iterate over the current map, static map instance, get all the references to it, and release the pointers to them. So ta-da! I really like this pattern because it allows you to do something that otherwise would be very hard to achieve in compile time, because we would have to list all the types that all the classes that you use in JNI, list them in some meta list. But there might be some types that, for example, user doesn't know that he's using because they're used internally, and he still will have to know about them and put them in some header, which is always at every compilation step is always parsed, analyzed, etc. Upkeeping such map would be cumbersome. On the other hand, there's using some purely runtime construct like the unordered map I pointed you out before, is simply much less optimal. Sorry, it's not optimal. It's definitely slower. I don't have right now the numbers, but this not maybe significantly slower, significantly faster, but still, especially in terms of accessing to the element, because we just need to return the reference after checking to atomic locks for statics, which are available for us since C++11. And more than that, using this way, we can check which kind of instantiations of our template were created in all the compilation units without doing any multi-compilation units entity like the list of all the classes, which is actually nice. So, okay, let's get to the last part, which I think is interesting. It's the compilation optimization. Since all the Java guys just went off probably anyway, so I'll just skip the meta part and let's do it this normally. So basically, I mean compilation optimization. I didn't say compile time optimizations, which would probably mean something that happens in the compile time that optimizes the runtime, right? No, I mean how to compile something faster. Actually, what? Why should I care about it? This is the compiler vendor stuff. This is my point of view about a year ago, I think. And after that, I started to think about it a little bit more. Because the main question is, who's your customer? Who's your end user? Of course, end user. Anyone who will use your software. That it means the compilation time does not affect the end user who just clicks your application, right? Or the customer that just to whom we just brought our binaries or services or something like that. He don't care about how long it compiles. But there's something very interesting that you should remember. When you write a framework, developer is also your end user. He will be very unsatisfied when using your framework. He will have to wait more than 2 minutes just to check his unit test when he's developing, right? So this is one of the reasons I hate Boost MPL, by the way. And if you use Boost MSM, which is based on Boost MPL, then you're just in a mess. But there's one more. You should also remember that there are some tired, underwatered, poor compile clusters that are doing your job. I was trying to do the perspective here. I'm not sure if you admire it, but I do. Let's just okay. So basically, what I mean by this is you have probably some compile clusters which just do the work for you. For example, we have in my current project we have some subsystems that are compiling by in summary to sum up all the cores that their time in order to compile something. If they would be compiled by one core, it would take about 7 hours or 8. So yeah, they can get tired. They use their Boost meta state machine. I hate them. So the thing is that you should care about it, basically. So what to do from the point of view of the build system? This will be just a general hint. It's hard to show you something that something specific in this area, but I think there are a few hints are worth to share with you right now. So first of all, use Ninja for a compilation. Yeah, really. In my very simple project, when I was testing, the Ninja seems to be 5 to 10% faster for a compilation than Make. I have no idea why, what they are doing, but this is awesome and do it. Use it. End of story, period. Second thing, this is actually an idea of my friend who was doing this for his own project. Well, when you have a multi-core environment, even if it's your own laptop which has 4 cores, it would be very inefficient if you would put the longest compiling sources at the end of your compile stack, because there will be one process that will work in the end in order to compile it, making the whole compilation longer, right? So what I'm trying to say here is that you really can save some time if you put the longer compiling sources at the beginning of your queue. Yeah, this can bring you, I don't know, up to a few 50%, maybe more sometimes, in a very bad for a very ugly cases, but still. So I was surprised by the how the compiler progressed in the meantime. I was checking I was working mostly on Clang 3.8 and GCC 5 and 6, and I thought that, yeah, changing to another version doesn't change much, but these compilers right now compete, so they're polishing their algorithms of compilation, and I think I've seen the results of 10 to 20% of compilation time speed up using the newer versions of Clang, just like that. So simply switching to a newer compiler can bring you really a really nice boost, actually. Using less generated code. This is actually this doesn't have to be a case in your actual code or source space, but usually a build system, in order to compile something, have to run the generator before anything he will do, because he have to know what kind of targets he will have to deal with. This means that this is done usually by one thread. And it has to happen every time that you start to build something, and it takes too much time. And if your generator, because generator is another entity that needs to be optimized, and usually it's not optimized enough, then it's just do everything again, and we're checking if there were any differences. That's the case of a simple, trivial code generator. So yeah, try to use less. That was also my motivation to not use them in my framework. So let's get to the source code. In order to make your source code compile faster, first of all, you have to do clean up your inclusions. Here's a nice example. Let's say that we have this piece of code, basically exactly this piece of code with yes commented include. So it means that just doesn't exist. So we're just compiling a pure main. So it compiles around, compiles around 0.7 to 0.8 seconds on my computer using Clang 5, something like that. So if you uncomment this time grows to about 25 to 0.3, just because we included something that we're not even using. And do you have any idea why is that? Well, I'll answer you immediately. I was very surprised by finding that iterator traits actually use boost MPL, which includes all the crap of code that has to be parsed, analyzed, and processed first by a compiler, just to find out that, oh, you are not using it. Yeah. So this is also important because in many cases, thanks to the ODR, it will also make your objects bigger, because they will have a duplicated content from different inclusions, which from the different templates that were instantiated a few times in a few compilation units, which then just start most of this work is just dropped out by the at the point of linking. Which I think the modules will help greatly, but still there will be some issues with that anyways. So I would like to change the clean up your inclusions to maybe never include more than you need. This is the basic. We had one of our projects in my current work, I was able to, just by removing that, there are some global headers that contain everything that you needed that are not precompiled headers, by the way, just the headers with all the tools that you need, and you include them because it's easier than selecting 5, 10 tools just by yourself. But I found out that in one of our projects I was able to shorten the compilation time about 15 to 20% just by removing one of them and placing the proper needed includes every time I need it. This is very simple. You just remove it, check where are the compilation errors, fix them, compile again, fix them, fix errors, compile again, and that's about 110 files. Oh my God, it took about a day. But yeah, please do clean your includes. The second thing, which you have actually scanned of here, was where the meta programming libraries. This one was actually made by me. This is a thought experiment, so it's not the fastest right now. but it's still good. So use something that is already tested and provided you by others. So there are things like Quasir, Meta, MP11. I think I forgot to mention also a Brigand. There will be a talk tomorrow from Odin Holmes that will talk about it a little bit more, I hope. He's got a lot to say, and inspired me to the whole subject actually. And what's more, don't use Boost MPL. Let me emphasize it this way: Boost MPL was totally important in terms of historical reasons because it put something that no one knows before in a way that they started to do meta programming, in fact. So it's very important to have this library in our history. But since it's using very ugly techniques and it's basically try to do something using a functional language to pretend that it's STD, like containers, iterators, things like that, made it very, very, very inefficient and slow. So anything, basically, when Louis Dion found out the idea of doing HANA, he presented HANA as also a meta programming library, and he pointed out that it's so much faster than Boost MPL. Well, there are some much faster than Boost HANA right now libraries in terms of compilation time, of course. So you should definitely take a look at them. And yeah. One last thing, and this was opening my eyes when I found something called MetaShell. It's a tool that is very easy to install when you have Linux, but just out of the box package, and it's basically a REPL for C++ meta code. REPL means that you have a console in which you could include your headers. And so this way you could load your code and test how this code is evaluated step by step. It has a debugger, so you can debug your bugs in your metacode rather than just dealing with the ugliness of compile time errors. Last thing, thanks to the MetaShell, I found a very nice bug in string library which I was using previously. Meta strings, which I was using, which helped me to speed up my compilation twice, basically, literally. Thanks to the fact that I was able to see what actually the compiler is instantiating. And it happened to instantiate something ridiculous amount of data. Thanks to this tool. The second tool is template, and this is actually just a hint if you will get deeper into it. It's a profiler for the meta programming, which shows you how much time compilers spend compiling certain amounts of code. But the problem here is that you first need to obtain the client code, then satisfy all the requirements, then get the template, patch the client code, put template into client code, and then compile it and have at least 20 gigabytes of RAM, because this baby is really, really hard to compile, to be honest. So basically, this is all I've got today. So thank you very much. Are there any questions? Maybe I will have answers. You've actually asked a very hard question. Why is that? Because calling JNI is expensive by design. So I've tried to write it so that it's as low. It doesn't add anything. Most of the things happen in compile time. So I don't have specific benchmarks because I didn't do the comparison, because basically, yeah, you just don't want to be ridiculous in terms of speed. But the JNI adds some performance cost. So So I didn't care that much, to be honest. I just didn't want. I just wanted to be minimal in terms of runtime. So this is my promise here. I don't have specific numbers for that. Are there any questions? Yes. Actually, yeah, I've made it. I didn't mention it because it will complicate the whole process. But basically, after every call to any method, you have to check, and normally you do that, you have to check if there were any exceptions thrown. So right now it's at the stage that this exception is changed into my exception and thrown as a C++ entity. So yeah, basically there is some basic handling of that special for a user. Okay. Are there any other questions? Okay, I think I don't see one. So thank you very much.